Hello, everyone. We're so excited to have you here. We have a great presentation today. It's going to be Ross Mitchell. He is a very qualified person, and we're super excited to have him. In just a moment, he is going to turn on his video and unmute himself and go ahead and give a great self-introduction. Ross, over to you without any further ado.
Thanks very much, Dan. My name is Ross Mitchell. I'm the Artificial Intelligence Officer at Moffitt Cancer Center. I've been at Moffitt now for about a year and a half. I came from Mayo Clinic. My background is computer science, medical imaging, and artificial intelligence. And a lot of the stuff I've been working on since I got at Moffitt has to do with translating technology over to the clinic. We're really focused on the implementation side and improving clinical outcomes and efficiency. And today I'm going to talk about one of the projects, one of the main projects I've been working on, which is using natural language processing to extract information from unstructured medical images or medical reports. So hopefully you can see the screen there. That's me. We'll get right into it.
Good to go. Yeah, loud and clear.
Okay, good. So some background. Much of the information that's used day to day in the care of cancer patients, is in the form of unstructured medical reports. And in particular, pathology reports are absolutely critical. Basically, there's a rule of thumb that says you don't have cancer until a pathologist says you have cancer. So the joke in cancer circles is if you want to, the fastest way to cure cancer is just to get rid of all pathologists, then nobody would have it. Of course, that's not too practical. And this is the kind of thing that they produce. This is an actual real snippet from a pathology report produced at Moffitt. And you can see that the language is complex. Starts off final diagnosis, lymph node, sentinel lymph node number 1, left suprainguinal excision, 1 lymph node, no evidence of malignancy. Wait a minute, no evidence of malignancy? That actually happens a lot in these reports. They just go through and read off all the tissue samples and report on all the tissue samples that they're given. And if you look at this report, they're actually going through lymph nodes one by one, and they're not seeing evidence of cancer. So they're noting that in the report. And it's not until you get to the very end of the report that you see, here's one with focal residual melanoma in situ. So this is a positive diagnosis. And the organ that's being affected is actually specified a little earlier in the report. It's part of the skin. So you can see that the language is complicated. It's not prose, it's very shorthand, and it's full of technical terms and lots of abbreviations. So processing this with computers has been very difficult, and the accuracy really hasn't been that great. But then in late 2018, Google published its powerful new algorithm, which you're probably familiar with, called BERT. And instead of referring to it by its long name, we just like to refer to it as the Muppet. And you'll see that a lot when you're reviewing the literature. And BERT is a pretty cool architecture. It spawned off literally thousands of applications and other papers. And this is a very high-level overview of the architecture of BERT. Text comes in the top and results come out the bottom. Within BERT, there are this particular version, there are 12 modules called encoders. I'm not going to go into detail on what they do and how they do it, but this is where the magic happens. All of these 12 units are interconnected. They talk to each other, and each of them is a very complex neural network in its own right. So the base model has 12 of these, and there are 340 million trainable parameters in the base version of BERT. And this whole unit is often referred to as the language model. And I think that comes from one of its original applications, which is translating, say, from English to French and so on. But now we do lots of different types of modeling with this base unit. So like I said, text comes in the top, and after it flashes through this model, what you get out at the bottom are a series of tokens, and we can think of this as a fingerprint that succinctly encapsulates or describes the input text. Now that on its own doesn't really solve any NLP problems for you. To do that, we tack on what's often referred to as an application head or a tooltip, and that will be trained to solve some particular NLP task. So then the fingerprint is passed to that, and it performs something like question and answering, one of the standard NLP benchmarks. So this has been a very, very successful architecture because of this split between learning the characteristics of the language and then training with less data tooltips to perform many different tasks, complementary tasks. And BERT set new records on multiple NLP benchmarks and for the first time achieved human level performance on several of these. So when we learned about this, I first learned about it in late 2018, just before I started at Moffitt. So when I got to Moffitt, I told them, hey, there's this cool new technology. I think it'll work for extracting information out of unstructured medical texts. And they said, well, it just so happens that's one of our top things that we'd like to have accomplished. So I've been working on that pretty much ever since. The goal of the project, very broadly, to see if we can get BERT to extract tumor site and histology from pathology reports. Why site and histology? Because they are critical for so many downstream tasks. When somebody's looking for a clinical trial, they'll want to find patients that have a particular type of histology afflicting a particular organ. And that's how the first step in finding patients who are eligible for a certain study protocol or a clinical trial. For administration, when they're monitoring how adherence to treatment pathways is maintained, they do that by categorizing into the histology and the site, the organ that's afflicted. So it's used for so many things downstream. And right now, a lot of that search is done manually, and it's very time consuming. So to address this, we had to tackle three major issues. The first is, how do we use BERT to extract accurate site and histology descriptions from these complex reports? Second, how do we handle the incredibly diverse terminology that's used to indicate the same pathology? And finally, just extracting the phrase isn't enough. We really don't want any downstream tasks to have to deal with language or text or strings. We prefer to give them a code. And the International Classification of Diseases, Oncology version 3, or ICD-03 codes, are what are standardly used in cancer care. It would be great if we could take these extracted phrases from the pathology report and turn them into a quantitative code for downstream use and alleviate those apps from worrying about language at all. So the first issue, teaching BERT the language of pathology, or extracting accurate site and histology, involves two sub-steps. The first is we have to train the top part of the model, the BERT language model, the language of pathology reports. It's English, but it's a very technical, complex English. The second part is we have to train a tooltip on the bottom there to do question and answering. So my thought was, let's ask questions of the pathology report. And the questions will be, what organ holds the tumor and what is the histology of the tumor? And to train this, we need ground truth. We need absolute verifiable truth. And for that, we turn to our Certified Tumor Registrars. And these are folks who, for a living, look at initial diagnostic reports, so brand new cases that present at the cancer center, and they read through the pathologist report and they abstract out a bunch of information. Of course, site and histology is one of the main things that they do, and several other fields. And this information is collected and used for all kinds of internal purposes, but it's also legally mandated that they provide this information back to state and federal agencies that use it for all sorts of things like tracking prevalence and incidence and using it for allocating funding. So we have a great system, and our certified tumor registrars are very accurate and very good at what they do. They run around 95, 96% accuracy, lots of internal training, lots of convergence. When there's discrepancy, they go over it and review and converge. So a fabulous set of ground truth labels. And this is what we used to train our BERT system. Like I mentioned, we're asking BERT to answer two questions given a particular pathology report. What organ contains the tumor and what is the kind of tumor? So to train the language, we started with Google's BERT. This is what they open sourced in late 2018, and this was trained on Wikipedia and book corpus, about 3.3 billion words. Now, a group in Korea took all of the PubMed abstracts available at the time, a massive corpus of text, about 18 billion words, and they did transfer learning or tuning of Google's BERT to create something they called BioBERT. And this BERT understands biomedical technical literature for medicine and biosciences. That's great. It's a great step towards our end goal, but it's not enough. And it turns out that a group at MIT then took 60,000 ICU encounters at Beth Israel Hospital. This is the MIMIC-3 data set, if you're familiar with that. So they took that data set and tuned BioBERT, So there's a chain here where we're teaching slowly the Google BERT and moving it more towards technical medical language. They called that clinical BERT. And all of those first three are public domain and readily available. So I actually started with clinical BERT, and I went and found pretty much all, or the team found all of Moffitt's digital pathology reports, almost 500,000 pathology reports, nearly 200 million words. And I used that to tune clinical BERT to create something we call pathology BERT or path BERT. Now, once we had trained path BERT, we still had to train a tooltip or a head to answer questions from the pathology report. And that also was a multi-stage process. The first stage was to use a very standard data set, the Stanford question and answer data set, the SQUAD data set. It's a very common data set used for question and answering training. So we used that in the first pass, and it contains very general questions. They're sort of like Wikipedia entries, and the questions are about the Wikipedia entry. So this is one of the more technical or more biological questions. What is the immune system? And then a description of what it is at a sort of a very high level, general scientific level. After training on that, we then went to the BioAsk dataset. This is almost 3,000 questions created by experts around Europe. And they're very technical, very biomedical, basic bioscience. You can see very complicated questions with a lot of complex terminology and a lot of acronyms. So we used that in phase 2. And then finally, we took a set of Moffitt pathology reports, 16,000 questions across 8,000 pathology reports. And these were carefully curated so that the distribution of pathology of sites and histologies in this group of training documents very closely matched the distribution that we actually see in the clinic here at Moffitt. And again, we asked of each of these pathology reports, we asked our system to answer these two questions: what organ contains the tumor and what is the kind of tumor? And it would hopefully produce answers like, it's a melanoma in situ and it's in the skin. So once we've trained this system, we still have this goal to transfer these extracted phrases and convert them into a standardized code for use downstream. And the codes themselves are quite complex, as you might imagine. I'm showing you an example here. This is from the SEER tables. The code 8070/3 corresponds to squamous cell carcinoma not otherwise specified. That's what the NOS stands for. And the SEER table, which you can get off of the SEER website, lists acceptable alternatives to the preferred phrase. And these are them for this particular code. But this doesn't even come close to encapsulating all the complexity you might see across a large number of pathology reports. So we complemented this going back to our Certified Tumor Registrars. We used phrases that they had typed in while they were doing the abstracting. So they would type in the phrase that they saw in the report, and they would also select the preferred phrase. So that allowed us to map complex terms in the pathology reports onto the preferred phrase. So we built a table, complemented the table from SEER with our own phrases that our CTRs had abstracted. And this is an example of some of them here. And you can see that these phrases are much more complex. There's a lot more words, a lot more terms, and just generally a lot more complexity. But the funny thing is, this isn't even the whole table. This is the whole table. Yep, 161 different phrases all mean the same thing: squamous cell carcinoma. And so there's enormous complexity here. And this is just one of 122 distinct histology codes. And on top of that, there's 156 site codes, and each of them have complex phrases, alternate phrases, and real world phrases that are actually used. So we went through and built this table, and then we screened our training data to ensure that at least one of these phrases was present in the report before it was allowed to be used to train our system. And that's because training the question and answer head required absolute ground truth. So we had to absolutely know that there was a correct answer in the pathology report before we could use it. And that's how we did it. We built this table and we screened. But in the real world, of course, you won't have that pre-screening ability. When we're seeing new reports coming in from the pathologists at their workbench, we're not going to have that ability. So to solve that issue and convert these phrases into the ICD codes, we actually trained a second BERT. We used that table that I just showed you, that large complex table, and we trained a mini version of BERT called DistilBERT to map those phrases onto the appropriate code. Now, if you remember from earlier in the report, we don't just get a classification out of this, we get a fingerprint. And this fingerprint, again, is a summary or a description of the text that's fed in. And this is actually represented numerically in the computer, of course, so you can think of this as a high dimensional vector. It's often referred to as the latent space. And if we look at just the first 2 dimensions or just 2 dimensions of this complex space, simplify it for our own visualization purposes, then the preferred term that we're interested in, let's say it's squamous cell carcinoma, going back to our example, that will have a particular location in this space, as will other pathologies that we're interested in, adenocarcinoma. But what's neat about this latent space is that alternate terms or similar terms will appear much more close to the preferred term than they will to another pathology in this space. So now we actually go through, after the system is trained, we use the latent space vectors and map them onto the closest preferred term vector in that space. So this is how we map this abbreviated squamous cell carcinoma onto the full squamous cell carcinoma. So this DistilBERT is essentially acting as a smart lookup table. And the reason I say smart is not only do correct alternate terms appear close to the preferred term in this space, but incorrect terms that have things like spelling mistakes or alternate word orderings will also appear close to the preferred term in this space. And so this is highly tolerant to things like changing the word order or having spelling mistakes. Okay, so we've got the whole system all together. So what do? We tested it on a sequestered set of just over 2,000 pathology reports with ground truth from the cancer registry. So each of these path reports were fed into PathBERT, which fed it into the histology, fed it back into the histology tooltip, and that extracted the phrases from the pathology report. These were then fed into our DistilBERT, which mapped them onto codes. And to verify this, we took the ground truth from the cancer registry and looked it up and said, did our NLP system manage to extract the same code and phrase that the cancer registry folks did? And how'd we do? Well, in terms of site, we did pretty well. Overall, our average is just under 94%. And this is on 2009 unseen reports. And this is, we've gone up 1 notch in the ontology table for codes. We've mapped 156 individual codes onto 52 group codes. So what you see here are the group codes. So breast is anything related to the breast, skin is anything related to the skin, and so on. And what's interesting about this is the 11 most common sites in this pie chart represent 82.5% of Moffitt patients. And on those 11 most common organs, we're actually running at 97.5% accuracy. So the system is performing well on the common cases, and it's performing less well on the rarer cases, on the rarer sites. And in terms of histology, we're doing even better. We're almost 97% accurate at extracting histology phrases and codes from the pathology reports. And in these pie charts, by the way, the size of the pie segment is reflective of the proportion of Moffitt patients, and the color of the segment is determined by its accuracy level. So reds and dark reds are inaccurate, and light tan and white are highly accurate. And you can see here, for example, adenocarcinoma, we're just over 97% accurate at identifying that from pathology reports. And adenocarcinomas are about 42% of Moffitt's patient population. Here, if we look at the 6 most common histologies, they represent over 92% of Moffitt patients. It's the vast majority of Moffitt patients. And here again, we're running at essentially 97.5% accuracy. It's really, really good, much better than I had hoped, actually. So, to summarize, we've developed a new tool that's a chain of different BERT systems to extract tumor site and histology from pathology reports. We've got really good accuracy. It's on par with human level performance, 94% accurate at extracting site, 97% accurate for histology, and even better than those numbers on the most common sites and histologies. Fantastic news. And just to remind you, this is a snippet, again, of what one of these pathology reports look like. And I showed this at the beginning of my talk, and I thought I'd bring it back up here because this actually was done by our system. This is not human output. This is output from our BERT system. It read through this report, passed over all of those no evidence of malignancy indications, and found and reported that this was melanoma in situ of the skin. So in this case, our system performed perfectly, got a perfect score on this particular pathology report. And that's really cool that it's learned to bypass all these various ways that they have of saying no malignancy, no evidence, no whatever. It's figured all that out and found the real case, the real positive case. So future work, we are going to train this with additional samples from those rare sites and histologies, and we believe that will boost the performance on those rare cases. And we've actually developed a very general purpose system here that can be used to extract information from pretty much any medical unstructured text, like a radiology report or an EHR entry. And it's flexible also in the sense that we just have to add new questions and train. We just have to retrain that question and answer head. And so we can ask additional questions of the pathology report. How big is the tumor? What's the grade of the tumor? And further, we can do transfer learning to create models for a specific organ or pathology. For example, we could run it through our BERT system and discover, oh, this is a tumor of the breast. Okay, let's train a system because breast is so common, it's such a large proportion of our patients. Let's train a model now specific to breast and ask breast-specific questions like BRCA genes, the breast cancer gene. Is that present in this report, and what kind of information is there about that? So this now opens up a whole wave of new applications. And that's everything I have. I'd be happy to take some questions and answer any inquiries that you might have about how we did this and what we plan to do with it. Thank you very much.
Wow, everyone, a big virtual round of applause for Ross. That was really great. Thank you so much, Ross. Everyone, if you're tuning in right now, stick around, do some networking, go check out the virtual booths. We hope to see you soon at the next one. Thank you so much.